Hey guys, in this video, we're going to be talking about gas laws and gas stoichiometry. This first section, we're going to focus primarily on the gas laws themselves as well as the ideal gas law. So first off, you need to realize that there are four key variables that we use to measure the physical condition of a gas. They are the temperature, pressure, volume, and the amount of a gas, typically expressed in moles. The first relationship that we want to understand is that of the pressure-volume relationship. Here we have Boyle's law. What we learn in Boyle's law is that the pressure and volume are inversely related to each other. If you take a look at this figure, you'll notice that as the pressure increases, our volume decreases, and vice versa. Another way to express that is to use the reciprocal of pressure with volume, and you see that now has a straight line relationship. So the pressure is going to be proportional to the inverse of volume, or the volume is directly proportional to the inverse pressure. Another common way that we like to express that is the initial pressure times the initial volume would be equivalent to a constant. So the final pressure and final volume can be set equal to each other, and we can solve problems using that relationship. If you look at the image on the right, you'll notice that in a physical setting, if you had a balloon at ground level and it rises up through the atmosphere, well, we have a high pressure on Earth, we have a low pressure in the upper atmosphere. What that means is that we will have a lower volume when you're on Earth, we'll have a higher volume when you're up in the upper atmosphere for that gas sample. Now, just to think about it, what happens to the pressure of a gas in a closed container if you were to double its volume while its temperature is held constant? Well, we now know the relationship that as pressure goes up, volume goes down, and vice versa. When we look at this specific situation, it says we double its volume. So the volume is going to go up times 2. Now, the question is, again, what happens to the pressure? Well, if the volume goes up, pressure should go down, and the amount that it goes down by is twice the volume. It goes down by 2 times its original value. Another way to think about that is it is halved, 1/2 the volume. So the pressure goes down to half what it originally was. Now, next thing that we want to look at here is the relationship between temperature and volume. When we take data, what we notice here is that as the temperature rises, the volume also rises. So we have a direct relationship, a direct correlation. The volume is directly proportional to the temperature, or the temperature is directly proportional to the volume. Thinking about that, if we look at this under standard conditions, we can actually rearrange this to be a proportion as the initial volume over the initial temperature should be equal to the final volume over the final temperature. Now, one very important thing to note here is that your temperature must always be in kelvins. The reason being, if we use Celsius temperatures, they don't truly represent the amount of kinetic energy that we have in that sample. So we have to have a sample scale that starts at 0. So again, we use kelvins because it will start at 0, meaning 0 energy. No energy, no kinetic energy is the starting point for temperature, right? Now, let's talk about Avogadro's law. This is our quantity-volume relationship. Now, recall, when we talk about the quantity-volume relationship, quantity we typically express as the counted number of particles, but it also could be the weighed number of particles. So you can consider this as either mass in grams, right? Or you could consider it as the amount, which we normally express as moles. Most common way that we're going to relate it is that the volume is directly proportional to the number of moles. So we give that the symbol N for our sample. And when rewritten, we can set this up to show the initial volume divided by the initial number of moles is directly proportional or equal to the volume of our final sample and the number of moles of that same final sample. Now, conceptually, you got to get this idea. If you had 3 times the amount, it would take up 3 times the space. Right? So just get that idea in your head. The amount being tripled would also triple the volume, the amount of space that it takes up. So in our figure here, we can represent the Avogadro hypothesis once more. When we look at it, we can see that we have 3 different kinds of gases, and when we consider the amount of the gas and the volume of the gas, there are some consistencies. So our pressure and our temperature are being held constant. They are fixed at 1 atmosphere and 0 Celsius. The mass of gas we see, well, the helium, we find that the mass of 4 grams is going to take up 22.4 liters. 28 grams of nitrogen takes up 22.4 liters. And finally, 16 grams of our methane will take up 22.4 liters. So the interesting thing there is that mass of gas, in every case, is 6.02 times 10 to the 23rd molecules, which means it's all 1 mole. Okay, so what we've determined is that 1 mole of gas, under standard conditions, will occupy 22.4 liters of space. Okay. Now we're going to work this practice exercise. Suppose you have a gas confined to a cylinder with a movable piston. So imagine you have a piston in here that can move up to expand the volume or move down to decrease the volume. And there is a sealed gas inlet down the bottom. So we have our gas particles that are going to be present inside of that container. Okay. What we want to consider for each of the proposed changes is what happens to the pressure of the gas. Consider the number of moles of gas, whether that's changed or not, and the distance between our molecules. So when we heat a gas while maintaining a constant pressure, so we're adding heat to that cylinder. If you think of the beginning condition, and we have our particles like so. We have our piston right here, and we're going to add heat. The new situation, well, as the particles heat up, they're going to start moving faster. They're going to collide with each other more often. But because we said we're maintaining a constant pressure, what will happen is those particles will strike that top plate and they'll cause that piston to shift upwards. So now the particles will be a little bit further apart as you break that down. Okay, so once again, if I consider part 1, the pressure is going to be changing. That's a constant pressure. Second consideration was number of moles of gas. That is also unchanging. We didn't add or remove any of the particles. But for number 3, in this situation, the distance is going to increase between particles. The distance goes up. Now, so our situation B, we're going to reduce the volume while maintaining a constant temperature. So we take that same starting scenario, and what we'll do is we will reduce the volume. So that means that the piston is going to shift downward, and we're going to reduce the overall volume. So thinking about that same situation, we had our scattered particles here. Well, if we reduce the volume, then those particles are going to move more closely together. Okay? The temperature is not affected, that stays the same. But when you think about having more particles in the same space, that will affect the collisions and the pressure. We're going to have an increase in the pressure based upon that change. Okay? So I guess maybe I should be explicit. Increase in pressure. It was a constant pressure in the last one. Okay? The number of particles stays the same. We didn't change that, so that one's going to be constant. The number of moles did not change. And then you consider number 3, the average distance. The average distance will decrease, right? So again, that distance between particles, we're talking about the overall volume that it takes up. If you decrease the volume, you decrease the space between particles. Okay? Now, our third situation here, in part C, we're injecting additional gas while keeping temperature and volume constant. So we have our original setting with the piston right there. We have our new setting where we still have the piston in the same spot because it's a constant volume. Temperature stays the same. So I consider the spread of particles. Well, in the beginning, I have a fixed number of particles. And if I start off there, remember that what we'll do is we're going to inject more particles through that little valve. We're going to push more in. So now there are additional particles. We increase the number and we will decrease the distance between particles as they collide. Well, since we have more particles colliding in the same span of time in that small space, we're going to increase the pressure in that container. We already mentioned that we're adding more moles, so we increase the number of moles of gas. And the final thing is the space between particles is going to decrease. Be aware, though, this is decreased distance between particles. It is not a decrease in the volume. The volume remains constant. Make sure you do your practice problem now, and we'll continue on. We're going to look at the ideal gas equation now. So the three relationships that we've explored to this point are Boyle's, Charles, and Avogadro's laws. In these three scenarios, what we can do is essentially we put them together, and we'll see that the volume is going to be directly proportional to 1 over P, so our P goes on the bottom. It's proportional to temperature, so the temperature goes on top, and it's also proportional to the number of moles, so the number of moles goes on top. In order for us to correct for the proportionality here, we add a constant R. If I multiply R by our current expression, we're going to see that the volume is going to be equal to, now not just proportional, but equal to that constant R times temperature times moles and divided by the pressure. The idea here is now when we've added this, we have a new form, and it's a little bit jumbled the way that you see it now. What we typically will do is we'll rearrange this by multiplying out the P. And the common form of the ideal gas equation is pressure times volume is the number of moles of gas times the proportionality gas constant R times the temperature in kelvins T, or PV equals nRT. We're going to be making use of this a lot. So something to consider. You add 1 mole of an ideal gas. An ideal gas, when we use that term, it just means that it obeys the ideal gas equation. We'll talk about some situations where some gases deviate a little bit from that behavior, but most gases can be considered ideal under normal conditions. So 1 mole of an ideal gas at STP, remember this is standard temperature and pressure. We're talking about a temperature of 273 kelvins and a pressure of 1 atmosphere. If it were confined to a cube, what would be the length in centimeters of an edge of this cube? Recall that a centimeter cubed is the same as 1 milliliter in terms of volume. So think of all the things we know. We know the number of moles, we know the temperature, we know the pressure. If we consider the ideal gas equation, we also know our constant, our R value. Now you haven't seen the value yet, so let me give that. The R value is equal to 0.08206 liters times atmospheres divided by moles times kelvins. Now, what we'll do is we're going to use that R value, plugging in these terms here, and it's interesting what you're going to see. 1 mole, that gets plugged in my N term, right? My pressure, 1 atmosphere, my volume can be determined. That'll be our unknown to this point, our volume. So volume is going to be R, P, N over P from the previous expression. Or if you're more comfortable, you can just have nRT over P. It's the same thing, just shifting those letters. Plug in the numbers that we have, 0.08206 liter atmospheres per mole Kelvin. Temperature at 273 kelvins. The N value was 1 mole. And our final pressure value was given at 1 atmosphere. So when we do this, we find that this is 22.4 liters of space, 22.4 liters. Now, since 1 centimeter cubed is a milliliter, we should convert those liters into milliliters. I'll do that. Recall that the relationship 1 liter is the same as 1,000 milliliters. So it becomes 22,400 milliliters. And since 1 milliliter is equivalent to 1 cubic centimeter, 22,400 milliliters is the same as that number of centimeters cubed. So we just said that this is a cube. Recall that a cube has a volume equal to the length times width times height, and those are all equal values. So really, our volume is going to be equivalent to the height cubed. If I do the cube root of volume, that gives me the height. So really, we just take the cube root of our 22,400, and that's going to get us what we need. So plugging that in, I get 28.2 centimeters as my height. So hopefully understood like the mental stretching that takes place there. But just get this concept. 1 mole of a gas. If you put 1 mole of a gas into a box, that box would be approximately 30 centimeters by 30 centimeters by 30 centimeters. You can again visualize what's taking place there. You've got a box. And 30 centimeters, just thinking that through, it's a reasonable amount of space that you can probably picture. So let's move on and talk about deviation just a little bit. Which gas deviates the most from our ideal behavior? Remember, 22.40, right, for 1 if rounded. This is our ideal gas value. So you've got chlorine that is a little bit lower than the expected value. Carbon dioxide, a little bit lower, but pretty close. Ammonia, just about perfect, as well as nitrogen and helium and hydrogen. So chlorine deviates the most. And what we find here is chlorine's deviation is based upon very strong intermolecular attraction, intermolecular forces. The rest of these have relatively weak intermolecular forces. So there aren't significant attractions between particles when they collide. Let's go ahead and do a little bit more practice. So first off, we have our sample 10.4 is using the ideal gas equation. Calcium carbonate is going to break down into calcium oxide and carbon dioxide. So what we want to do is we want to identify how much carbon dioxide is generated based upon some measurements we've collected. We find that the CO2 is in a 250 milliliter flask. The gas has a pressure of 1.3 atmospheres and a temperature of 31 Celsius. Question is, how many moles of that CO2 gas have been generated? So we consider the ideal gas equation. PV equals nRT. We're trying to solve for N, so rearranging that gives us number of moles is pressure times volume over R times temperature in kelvins. A few little modifications that we're going to make. This 250 milliliters is going to have to be put into liters. It'll be 250 liters. Also, 31 Celsius, that's not in our standard kelvins unit. We need to modify that as well. We'll find that adding 273 to our 31 degrees gives us our Kelvin temperature, 304 Kelvin. Now, plugging in values and doing the math, we're going to see that our pressure value, 1.3 atmospheres, multiplied by the volume that we have here, this was a 0.250 liter flask. Divide it by our ideal gas constant, 0.08206 liters times atmospheres over moles times kelvins, and multiply by our temperature, 304 kelvins. Plugging that in, multiplying and dividing, we find our mole value is 0.013 moles of carbon dioxide. So, hope that one makes sense. Go ahead and do the practice exercise for 10.4 now. In sample 10.5, we're going to be calculating the effective temperature change on pressure. So we have an aerosol can. The pressure in the can is 1.5 atmospheres. And we find that that is happening at 25 Celsius. So there's my temperature. Assuming that our gas obeys the ideal gas equation, what's the pressure? My goal is to find the pressure when our can is heated to 450 Celsius. So this is a little bit complicated. You've got more than one temperature in here. We're going to have to think about this from a little bit of a different perspective. We need to consider what we have, consider where we're going, and then choose which of the gas laws makes the most sense. Well, our goal is to find a new pressure at a new temperature. We have a starting pressure with a starting temperature. We didn't talk about this law specifically, but as you increase temperature, you will increase pressure. This is similar to the way Charles' law works. The initial pressure divided by the initial temperature be equivalent to the final pressure over the final temperature, since this is a direct relationship. So our initial pressure and initial temperature term, our final pressure and final temperature term can be related that way. Please remember that we have to go into Kelvin. So my 25 Celsius turns into 298 kelvins. My 450 Celsius, adding 273, gets us 723 kelvins. So plugging into our expression, our 1.5 atmospheres should then be divided by our 298 kelvins. It'll be set equal to our unknown P2 over 723 kelvins. And when you solve, 723 multiplies up by 1.5 atmospheres, then you divide under by 298, and our final pressure comes out to 3.6 atmospheres of pressure. Do that practice as well, and we'll move on to 10.6. Now, to this point, we've seen several gas laws. We've seen relationships between pressure and temperature and volume and moles. But we have another unique instance called the combined gas law. And the combined gas law exists when you have a fixed amount of gas, but you vary the pressure, volume, and temperature. If you look at the relationships that we have, the pressure, remember, is inversely proportional to the volume, but pressure is directly proportional to the temperature. So our setup should be P1 times V1 over T1 is a constant. And if I change these values, the new pressure, volume, and temperature can be expressed here. Now, it helps sometimes to rewrite this in a form that isn't fractional. So you can multiply up the temperatures to the opposite sides. That can be re-expressed as P1 V1 T2 is equal to P2 V2 T1. So reading this problem, we're going to be using this relationship. An inflated balloon has a volume of 6 liters at sea level. So I've got volume, I've got pressure of that sample. It is allowed to ascend until the pressure is 0.45 atmospheres. During the ascent, now be aware, ascent means, again, it's rising up in the air. That is ascent. The temperature of the gas falls from, so this is the starting condition, 22 Celsius to negative 21 Celsius. Calculate the volume of our balloon in its final altitude. So, identifying and breaking down everything that we see. Well, everything I've highlighted in yellow is the starting condition. So, I've got a volume initially, I've got a pressure initially, and I have a temperature initially that I'll modify by adding 273. We're going to find that 273 plus 22 gives us 295 kelvins. The next thing that we're going to want to do is modify and identify what we have here. Well, that T2, add 273, you're going to get 252 kelvins for our T2. The volume is our unknown, that's V2, right? And then this 0.45 atmospheres is the ending pressure, so we're going to call that our P2. So I have all the information organized. I just need to use the expression to solve. So we plug in what we need, and I can rearrange this expression right away so that I have it set as a fraction that'll be easier for me to use as I solve. My V2 is what I want, so I divide the P2 and the T1 under. V2 will be P1, V1, T2 divided by P2, T1. Plugging in our values then, you have 1.0 atmospheres as your P1. V1 is 6.0 liters. The T2 was 252 kelvins. And we divide now by our P2, which we identified as 0.45 atmospheres. And our T1, 295 kelvins. So doing the math, we end up getting 11 liters as our final volume in this problem. So work that problem out as well, do the practice, and then we will move on. I'm going to wrap up this segment of the video now, and we'll continue in part B.